Let me continue by recapitulating where I stopped yesterday. Again, as is the norm, this is taken from what I call engineered airflow intelligent cooling by what I call degree centigrade controls from 2004, and it has been presented very extremely well, and in general it covers what I feel is important for a designer to try and understand. Again, one more time, you must remember that these people have had probably 30 to 40 years experience, and if you remember the earlier the same slide shown earlier, experience seems to be at a premium. That is the reason while everything is available out there for you, you still have to depend on a professional to do plumbing from you. Maybe electrician, yes, plumbing, call him, you have no choice. Same thing with any other thing, including tailoring. So obviously every person has a beautiful brand new machine. Not many people make their own clothes because designers and merchants are out there to change the designs. So coming back to my slide again, these people have suggested one very simple way is you must have an authentic pressure versus flow characteristic of a fan. It's not what do you call, it is not that easy to determine that one particular piece which you have been using. The simplest way of doing it is make your own setup. It is not an impossible thing. You see here you have a small chamber like thing here, not chamber like thing, it is a chamber. Depending on the thing, sometimes it is circular cross section, sometimes it is square, because square is easier to make, and then you can always open the top and then play around with it, and then the fan under test is here, okay. And then there is a small orifice, and then you have some other what do you call paraphernalia here, another fan and so on. Issue here is we need to somehow plot this curve, pressure and change in pressure versus airflow, and this is where we end up with real life conditions. What is the voltage with which you are operating, and related to that is the frequency also. Imagine most of the small motors are very much dependent on both the voltage with which you operate and also probably the frequency. While a larger motor, it is very easy for us. For a smaller motor, especially if it is AC, you need close control. If it is DC, to some extent somebody has done this experiment for you, and that being a DC motor, life is relatively easy, because DC motor you have only one simple parameter, increase the voltage, it works well without any problem. In the case of AC, you need to characterize this, and then this is where things come. A small change of it sometimes makes a curve which is significantly different, and it may or may not follow like this. For all we know, sometimes it may cross and come over here. Small change in similarly a little lower voltage may lead to other things, and there is also self heating. When you run a fan, something happens, both two things, one is happens to the motor itself and happens to the air all around like this. So if you have an authentic curve using this plenum chamber in this, it is very much possible for you to plot these things. Similarly, the much more important or difficult thing for you to probably difficult for you to plot is to have the equipment system resistance, which if you ask me is, even if you have measured it, it is a little dicey, because very rarely the final equipment can be directly used here. You still have a scaled down model, and then whenever you have a scaled down model, these principles of dynamic similarity apply. So only to a certain extent you can probably make a scaled down version or even a full scale mock-up. So if you do the same saying, if you find out the what do you call change in pressure from 0 to maximum by adjusting the turn in flow, measure PQ and calculate Q and plot Q versus delta P curve. It looks easy. After that you superimpose one over the other and everything, no, miraculously everything works exactly. There are not many miracles that happen. You have to make your own miracles. So, we see here, if you have, obviously we have this B is a beautiful good what do you call a nice and properly laid out equipment. So, in a properly laid out equipment you have ensured that the static pressure for a given airflow is very less, and improperly laid out equipment ends up with this, and this may be something our bad luck, because Murphy is at work. Murphy is not at work only when you lose a nut or when you are otherwise there. Murphy ensures that we end up with these funny things, and anything you do to improve any other heat transfer seems to interfere with these things. If you put more fins, what was perfectly fine and started, it has moved that side. And then if you try to add baffles to ensure that your air is properly channeled over your hot surfaces, you may even end up here, by which you do not know where you work with. So, again if you recollect, the very first picture I showed you a video game in which there is a big fan, probably it was an 80 mm fan, then we have a heat sink, then they have put a beautiful manifold like that to spread it such that the heat sink there. I will just show it the other way, saying you have a fan here, then you have a heat sink here, then we have a manifold which is blowing everything, and directly in front of it you have the main device which is also there, and obviously it does not go. Then what did they do? They had to mill the heat sink in a particular way so that the air can go away like that. Now, all these things, there is no simple way of modeling and calculating it. So, what people do is they try to make a CAD model. That next picture, if you remember, shows you what to do with it. So, if you I will see if I can insert it afterwards. We have this issue of smart design. It is not about the new type of smart design, but what we are talking about is being smart in design and eventually trying to put proper sensors and all. Can we simply increase airflow as power increases? It is obvious, it is sort of a rhetorical question saying yes or no, and cost we also know, no, sadly cost is very much around. And next things, though he says a quick summary, it is not as quick a summary as it is. You have seen here. Type of fan, tube axial, vane axial, blower, operating point on the fan curve, size of fan diameter, speed of rotation, density of the gas or air. So, most of the time luckily we use normal whatever ambient air is there, but once in a while you may be forced to dry the air, or you may be using a chiller in front of it, by which marginally it changes things. So, we have the speed of rotation, faster obviously you get better flow rate, and then right now we have the issue of efficiency of the whole system. As we are working for more and more the change in going green, we need to consider about efficiency. It is not just about peak power or peak torque or peak blow or anything like this. So, they have given so many things here. Okay. I think those things are all, considering a point of operation on a fan curve, it is possible to derive some simple scaling laws between change in pressure, the total wattage, then the speed and the diameter of the fan and so on. So, and rho for a fan, you can read them here is a function of this and this, saying diameter is large and the speed is more. Delta p is again a function of these things, and he has shown that Q is independent of density. Therefore, fan at sea level 2000 meters has the same Q capacity. Fan mass flow rate varies with altitude. Q varies linearly with altitude. So, there is something about the differential pressure, then there is a pumping power required, and then the total, if you ignore electrical efficiencies, suddenly something else has come into picture. You have seen this. Fan motor itself has a resistance, and which slightly depends once again on the speed of operation, back pressure and so on. So, we have this pressure and power characteristics, and some nuisance which is getting real. Actually, if you are stuck in a room where a lot of this equipment operate, we end up with sound, too much of sound. So, it is real. You have no way of getting over. Just sticking a fan in the airflow path, and compared to what I have told you, make it face a load. If there is a hot component, you make it face that, does not seem to cure all problems. One problem it solves. One problem is it makes the peak temperature less. Actually, it has no that much of direct control on peak junction temperature, as much as cooling the fins of the heat sink. Once the fins of the heat sinks are cooled, a lot depends on fin efficiency. So, at very high velocities, if you take a standard normal extrusion, fin effectiveness comes down. So, with that, beyond a certain point, that is where Schoenhauser mentioned, do not exceed 6 meters per second. Beyond that, no, it does not seem to make any difference, except it is already neatly packaged and so on. So, they have given things like noise is dependent on speed. Okay. Next is engineering implementation or the 4 fan laws for sound, then the total amount of discharge, total amount power dissipation, and then total amount of static pressure. We want to increase the discharge by 25%. To increase, we increase N by 25%. You see here, pumping power seems to go up by 3 times. Fan pumping power now suddenly has become doubled. What was 1.25 has become such a horrible this thing, 95%. Sound power level increases 3 times. So, now comes the trade off, saying what do you do? So, from sound law can be expressed in decibel form as change in sound power from level. So, huge this thing is there, though he says 5 dB difference in sound level is noticeable. Acoustics talk about a 3 dB thing. 3 dB is sufficient for most people to feel uncomfortable. From existing thing, a perceptible difference is 3 dB, especially in the silent this thing. So, as we keep going on, we end up with all this funnier and funnier relative nuisances. So, big this thing is given here, saying what happens to if you increase in speed, if you increase in this, if you increase in how much of power increases, the power demand increases, and then the noise level increases, while the pressure level is just going up about double, while the total discharge is just increased by 75%. We end up with all these undesirable things. Follow? Tremendously undesirable factors. So, this is probably the sum up of all the things related to fans. Doubling the speed increases heat transfer coefficient by 62% only. To remove more heat, airflow should be doubled. Doubling airflow causes delta P increases by a factor of 4. Power required to double airflow is so much, 8 times. Sound level increases by 15 dB, it is a lot of thing. And then something which we forget, fan itself deteriorates drastically. So, it is not just enough to add a fan, we have a problem, you can just marginally increase the speed also, it is not constant. This is where the what do you call, people who have that experience, they have said this is what, okay, increasing flow rate beyond a certain value is not worthwhile. Murphy's law for electronic cooling, optimize your design, heat removed pumping power, smart thermal engineering is true for devices, boards, chassis or data rooms. Cooling devices, you would have noticed long ago, the what do you call, chips themselves, we have a little problem with the chips. Next come, how do you cool things? Is it just about simply increase conduction or increase thing, or do we now talk about phase change, or do you talk about Peltier mechanisms? Things like heat pipes seem to go in and out of fashion. They come to fashion, they go out of fashion, they come to in. As of now, you can't beat simple conductive heat transfer from the chip and a little bit of better geometry on the chip, including mounting it upside down. And some of you audio enthusiasts may remember the old audio chip. This is a 8-pin dual inline chip. I am sorry, 16-pin dual inline chip, and the center 2 pins had a tab. So, you have a dip package with 2 small tabs which are thick copper plates. Thick means maybe 1 mm or 1.2 mm. So, I will just see if I can make it to a little bit of circus. You have this package and 2 of these things are spread out, then there are holes and you can mount the whole thing onto a heat sink. One of the earliest thing, this typically was called the CA810. CA810 audio chip probably was designed sometime in the late 70s, and the package itself became a very popular dual inline package. Then later on single inline packages came about. So, some of the new audio amplifiers and all, everything is single inline, and you have nice beautiful heat sink like thing on one side. They come with multiple pins. The smallest multiple pin is probably the TO220. Earliest on in one of the slides I have shown you, there are things which have even 12 pins and all in one line. So, there are special packages, all of them have a beautiful mounting thing, and if there again we end up with a very peculiar thing. If you give a mounting hole, you will spoil the contact area. If you do not give a mounting hole, how do you mount it then? So, all the variations I can think of are there. Next comes to boards. Board itself, is there a way you can do, you can increase the heat conductivity of the board, and as I told you, at one extreme we have metal boards and then we have the chassis. Okay. Chassis means usually that what do you call, the unit in which you mount, then the whole room. We are very strong in these devices, we are maybe a little okayish with the board and heat sinks. Now, we come to the important thing. When you have the large room here, you understand, we have a huge room, and when we have rows of racks, any of your small thing will help only so much, and then even maybe a rack. Now, how do you cool the rack without freezing the poor operator? Now, we are in the modern world. So, it is not, it is okay saying they are dispensable, they are indentured labor. So, they are not dispensable, you cannot train one and you cannot get it. So, now the cooling of the racks itself, it is done very well. I have a picture of a solar installation outdoors. When I retrieve it, I will show it to you. It is done extremely well, and room cooling is isolated from the that what you call installation. At this point maybe it is appropriate for me to mention that if you go around and see these cell tower installations, sometimes you see there is a small enclosure and you have a panel mounted air conditioner. We have two air conditioners, we all know. One of them is the window air conditioner. Window air conditioner, there is a rectangular box like thing. Part of it which is not visible to you has the condenser, and the part which is visible inside the room has the evaporator and all that. This is the window air conditioner. Then we are all familiar with split air conditioners. We have an external unit and indoor unit. Now these panel mounted air conditioners are very similar to these things, except that you have a flat panel which is fixed on either the side or the back of one of these racks, and the whole rack is sealed. So air is taken from inside, the evaporator is fitted as a part of the panel. Depending on the design, the evaporator is sometimes on the outside itself, or it may be a long box. So the air is passed through that, and then continuously air it keeps cooling the air, and then at the little towards the topmost post of it you have the condenser with a fan outside. So internal working fluid like dry air is isolated from the external air. You can see this occasionally on installations outside. Now anywhere when next time when a cell tower is being opened and checked, I suggest to have a look. If possible, I will try to have a look at it. Okay. The earlier thing is just make a better fan, but are we ready for a better fan? The military, if can afford it, and others can afford it, and then the moment you have, we end up with ending up with larger power supplies, and then overall or put up with lower life, and we have this big nuisance of electrical and acoustic and electrical noise filtering. It is real. It is just real. Beyond that, at this point I can't comment on that. So we have here saying this, we have the design process, architectures, failure, designing for reliability, design validation and testing. This is where it looks like only space does this thoroughly, and aerospace, aero people are able to do a certain extent, but right now even when you talk about a small thing like a mobile phone, you probably have to go. I will just show you. This to me is a wonder. Understand? I have this small beautiful hearing aid. It costs a lot of money. Okay, it is really a lot of money. Sir, can you focus it on this? If it is possible to zoom. You have seen this. This small device has everything I can talk about. Okay, good. And you see this, I am sure all of you have this, carry this nice fashionable watch. This is the tracker. It tracks my health and my whereabouts to other people have a stake in me, other stakeholders in my good health other than the insurance company. Obviously, a lot of people need to know about it. So, if you see all these small things, lot of this design process, architecture, failure, designing for reliability, design validation and testing have gone into it. Because it is not just about if you fail I can repair it, it is about increasing the reliability over the time to quickly try to recover from a thing. So, this is what I tried to tell you about it earlier. In a push system, you see the airflow distribution directly, airflow, much more air is here, and in the other thing it is a little lower airflow distribution. This is only a illustrative example like what you are likely to see on your shampoo ads saying creative visualization. The model, the girl or boy may or may not have it, everything could be shopped, p-shopped. So, this is also one of the creative visualization, but is as good as a this thing here. Just to illustrate it, lot of air flows in the direction we wanted. So, it is possible for us to decide which way to mount these things, and in this case luckily this I mean it looks like almost a laminar flow thing for a pipe, which is not true, just they are showing it. So, you can decide where to put what in these things. You have seen this here, very important. I had mentioned to you in passing. Pressurized system, clean air, low fan operating temperatures. You understand, in the case of the push design, main thing is directly you direct air, and fan itself is seeing ambient air which may be cooler than the exhaust air, and this whole system, very important thing in the whole system is the whole system is under positive pressure. Seen that thing, which happens if you go to most clean rooms and all that, they adopt that system. This whole chamber is positive. So, to the extent when you open the door or even there are small gaps everywhere, air blows out of the gaps, and any air pressurizing inside is filtered neatly and it is kept pressurized. So, unwanted dust and outside thing does not get tracked into the space. I hope you appreciate the point. Whenever you push this, when you have the inlet air pressure which is coming here, this whole thing is under positive pressure, and the color depends again visualization about cold versus hot, and you see here everything is cool, and you have a filter in which you have slightly different better control over it, but the con is airflow is not uniform. If you have so many of these racks and then you have a fan here and a fan here, I am sorry, so many of the PCBs, you have a fan here and fan here, we do not know where the air is flowing. You have really no strict control on it. Localized filter. So, if you have a square filter and if you put a small, if you have a square filter and you put a small fan in it, you will see that the air does not get enough gap for development of the flow. So, you will have a nice patch, and remaining it will still be not useful. Then you have a air leakage issue here. While it looks nice, the smallest gap, or in our case let us say you have a connector, or let us say you have a switch, or you have access somewhere one thing. These things, any small leakage will allow the air to escape. So, we have a problem there, and he calls it flow deflector. You end up with almost trying to use aeronautics and I am sorry, QFT and those things to push air. If you do not use that analytics, you will end up with trial and error, fit and see, blow and see what it is. So, while it is complicated, the professionals are there who do it all the time. Okay. So, now we come with equally interesting thing, saying can we have radial fans with a pull configuration. If you remember, I have shown you the two circular fans in the center, there is an inlet and exhaust is there all around. It is a simple radial fan which goes in all the directions, sucking in. So, and then it throws it in all directions. Now, we have here, if those fans have an involute housing, if you make an involute housing, it will become like a regular blower, a little like the blowers you may see at home in your kitchen, that what you call hood. So, if you have a hob and you have a hood about it, there are very simple ones which have only a small one or two fans stuck. There are very complicated ones which have these extractors which have these what you call special involute casing blowers which are attached to it. So, we have here the advantage inherently about these things is it can handle a higher pressure for the given other parameters, again no, they also take a lot more power, high flow, exhaust direction change. So, it is possible for us that we can play around with which way it is. That is what I was telling you about lower recirculation on fan failure. In the unlikely case, if the fan failure means not dead fan, it will start running slow. Inside, no, the chances of things getting circulated are poor. Low fan density, large flow drop and failure, expensive, unfiltered air leakage. You see, if you see the whole plenum is under, that whole cabinet is like a plenum chamber. It is of the lower what do you call air pressure than outside. So, first thing that happens is it acts like a vacuum. Anywhere there is a small gap or anything, or you have forgotten let us say you have a potentiometer for adjusting something which invariably comes with a cap which has to be closed, or you have a connector which already has a cap. Not all connectors are fully IP67 sealed and all that. So, anywhere these gaps come, air keeps going off inside, and power is reality. You have power cables, and then usually you have various types of what do you say, I won't call it a full fledged what do you call bus bar, but you have places where the cables have to be inserted. All these places are, they will suck air. So, we have this problem as it is not just about air leakage, it is about unfiltered air getting inside. So, we have, while that was shown with you see the previous thing is about radial fans. Now, with axial fans, it seems to be very easy to manage. All you have to do is take the fan which was originally at the bottom here and then remove it, and then I am sorry. Hey. Yeah. What was originally at the bottom, take these whatever fans here and just put them on top, put a space here, and you can buy these fans off the shelf. And I expect that the ones what we get now are the 100, 120, 110 fans. They are little about the size of a CD. So, they do not cost too much. In our Indian rupees, a good metal frame fan probably costs us about 500 to 600 rupees, and which works directly on the AC. So, you can maybe 10 US dollars. So, you can stick as many as you like all around. Better flow uniformity, the flow can be controlled, and most important is filter usage efficiency, because while here the pressure drop can be like this, as it comes down all the part of the filter can be directly used, which is good, is it not? So, now if you see here, in the problem here is there is a space that is required on top. The previous picture, not much of a space was required as such. If you remember, yeah, see here it is only limited by the total gap of the fan that is available. Only for convenience, and it is not to scale, he has shown all of them now about the same size. Other than the fan proper itself, no, this much extra place is required for us, and whenever there is an attempt for the flow to turn, you have a small problem here. One of them is, this is already at a slightly positive pressure compared to this area. So, this fan, no, the way we arrange them, whichever way you try to arrange this space, there is always a compromise. While loss due to flow turn, loss of a fan leads to large recirculation. So, I am not very clear at this point why, what I expect is, in the case one of these fans fails, so the air does not behave the way we want it to behave. Fan plus plenum height is comparable to radial fan model, which is what he has shown. Fan C is the high temperatures. You see here this red, already the hot temperatures are all seen by the fan. So, the next slide talks about, can we have a compromise? Can we have a push pull design, saying you have something pushing here and then something there, and like all other what you call design considerations, it is still a hodgepodge and a what you call compromise. So, airflow you have some control, slightly higher reliability, though I would like to what you call contest that, because the more devices you have, chance of its failure are little higher. But in the case of a fault, there are still parallel things operating, which happens with nature. So, you must have heard of something called sympathetic circulation, which happens to when people have a heart problem. Suddenly they discover that they have been living with it for let us say since 50 years, then they will say no, you had this as a at a young time, and then nature has compensated and it has given you alternate circulation, hence you never noticed it. Now, when you come, you have this. So, coming back here, the pressures between this and this can be improved. Fault tolerance is about that, and then high pressure capacity, because we have full control on it. On one side you are blowing and one side you are what you call exhausting it is there, but main thing is extremely expensive, and contrary to what we think, it is not as easy to control as we think. Where do you put the sensors, where do you put the what you call vane switches, and how do you take care of temperatures, and which one do you switch on and which one do you switch off is not known that well. And here this is more for what you call, I will not call it a filler, it is nice for you to know, so I will gloss over it. All it means is, if you have an airflow, there is a filter, and if you leave a gap, there is a place for it for the flow to develop. Okay. So, lots of things are there about the thing about drop in pressure versus what you call the discharge and so on. No? In case you have no filter and filter location is far away, how these things behave, lot of these things. So, any filter degrades fan performance, which I mentioned in passing earlier. Performance degradation increases as the filter is moved closer to the fan, because smaller and smaller area only is available for you. If you were to shift this thing here, it gets worse. If you put a little more gap and make it back here, it is better. Pull systems with filter installed in inlet yields best. Fans see only filtered air, which is a beauty compared to other one. Just like you have this thermal heat issue, if you were to keep the what you call filter here, fan is relatively cooler this thing. So, when the fan is rotating, all the dust gets settled here. So, maintenance is a little less. So, we have that the same thing is maintained here. Filter degrades fan performance, leakage does not affect fan performance, cannot be used for pull system, fan is unfiltered air. So, you have the advantage and disadvantage. This you probably would have noticed, in case you have a exhaust fan in the kitchen, it always gets coated with grease. I think you have taken all possible precautions, but then you know the reality, grease is real. The same fan, when it is used in your restrooms, toilets and all that, you do not have the grease problem as much as you have other problems. So, the specifications and all are significantly different. So, these are all been plotted saying filter located downstream, upstream, the gap and no filter, how discharge changes with so many what you call centimeters, I am sorry, he calls it 0.17, I am not familiar with it. I expect it is about 5 millimeters water. Okay. Now we come to very first what you call changing, fast evolving what you call things. So, we have nice computers. He has made, I feel, no off the cuff statement saying computer simulation helps eliminate most thermal problems. I do not agree with it. At least it knows where the problem is, and then next stage of optimization of positioning, all this does solve the problem. So, I mean airflow and thermal assumptions very key result to quality. So, garbage in, garbage out. So, unless you know the actual heat transfer coefficients, actual performance, everything, and main thing is this, what if conditions. If I put more spacing, how does it happen, what to do and all that. So, I think like that they have shown something which is simulated. Why I feel emboldened to show this is, we have done a similar thing in the case of one of the early what you call telephone exchange racks in India. So, maybe it is a lot of what you call control of a cooling management system. You have diodes and what you call fuses, and then you have filters, we have regulator, microprocessor. Coming back, you see here we have a computer simulation which I will repeat again, does not what you call really solve problems, but it can test what if conditions, saying if we do this, what will happen. So, in the case you see here they have put 1, 2, 3 some devices which will the configuration, and we come here slowly, various types of things, saying thermal management system consisting of a power regulator and the actual fans, then you have filters, and these are all some backup things, saying in the case of something what will happen, especially to prevent, they have given a diode logic here. So, you can in fact have two dual two power supplies. So, one of them will come, then this microprocessor is attached to the host interface, where it will take its input from various sensors which are mounted. So, next picture talks about fan voltage regulator, then tachometer signals, meaning they are showing the what you call what is the speed of the fan, and very critical thing, they are only using simple voltage control from the fan. We are coming into some assumptions, saying individually fans can or cannot be controlled. So, we have only a single fan voltage, and then the microcontroller gives you changes the voltage irrespective from something, and runs the fans a little low, I mean a slightly lower speed or slightly higher speed. So, we have here, he calls it 3 wire, the succeeding pictures explain. Control input signal, analog and pulse width, TAC output, speed control through control signal, precise individual speed control is possible. So, what it is done here is, each fan you have seen that control signals are there, and individual fan voltages are measured here. Instead of the fan having only 2 terminals, each fan now is capable of having 4 wires. It is used normally in electronics whenever you want to take a measurement of even a resistor, to prevent the leads from affecting that, you have leads directly at that point. So, instead of taking something here, you need to take for everything, you end up with 2 leads. So, if you have a full 4 wire system like this, you have much better control. No power regulation is required if voltages are available here, internally regulated. Only problem is expensive, somebody has to work on it. I feel it is more taken as a challenge by this company, but tough. Yes, in this input range can vary, fault tolerant, and something very important is hot plug-in, meaning when the equipment is running you should be able to add or remove fans. It is a little tough. If you have some redundancy and if you can at least know things can hold on for some more time, meaning as you remove a fan, maybe you have access everywhere and you can divert it, you should be able to quickly have another fan not running or ready to run, remove it, push it in and start up, and the whole thing should be operated very quickly. I expect it should not take more than around 5 to 10 minutes. Typically that is the time required for the whole system to malfunction. We have this tough about I am not very clear about what this switching is. It probably means cutting in and cutting off of the fans, and then we also have this stuff about inrush current. So then commutation noise suppression. So in case you have DC fans which are commutated through old brushes and all, or even with the electronically commutated fans, obviously we have a little issue about the fan motors themselves now may be altering the various characteristics of the rack. So they have all this stuff about a fan voltage regulator typically for this, and contrary to our popular what you call intuitive reasoning, motors never fail due to low voltage. Not many people appreciate it. They say voltage it was there is it failed, and in fact motors are capable of operating up to a certain lower voltage. Below that they fail, but higher voltage is catastrophic. Immediately the things burn. So we have a fan voltage regulator, and then we have so many of these circuits saying buck circuit and so on, which I feel is too much of thing, except for actually students who work on this. That company obviously is able to have that voltage buck boosters and all that, then voltage booster, and I will just quickly just show you. So we have so much of or then even power he is giving a parallel voltage thing. This is a general design saying you maximize reliability of components and blocks, short term recovery paths for failure, series parallel design, monitor faults and enable service, fan failure prediction, filter blockage in power control. This is very much very possible for you to do. Airflow rate, maximize reliability, immediate service, failure prediction, enable scheduled maintenance. So this looks almost intuitive, and you need not worry about it, saying we have so many what do you call monitoring flow resistance, temperature rise, pressure drop across filter. These are all very much possible. Cooling capacity monitoring. So all of them it is very much possible for you to detect. So he has given their own obviously a patent device which I have no comment on it. So we try to do, when somebody needs to take data room device board equipment chassis and then work with all these things, operating flow, heat sinking parts. This is something I would like to show things. So we have here so many what you call data acquisition systems, and that small one is it's a small turbine. So both types are there. There is a hot wire anemometer and axial anemometer where there is a rotor which is turning. I can't make out whether it is a hot wire anemometer or a normal what do you call simpler turbine anemometer. Hot wire is a little sensitive, both to external factors and this, but extremely sensitive to temperature, and a regular turbine type anemometer has a beautiful thing. So, we have some way of airflow sensors mounted all over the place, and then we try to measure and calculate airflow and so on. It is nothing, that same sensors have been mounted, somebody has tried to plot it. So, we have products, and we have heating and ventilation. In the case of military, I expect that this is probably camera which is mounted somewhere, and then we have medical devices, then we have telecommunications, and then I am not very clear what a critical facility is, that is a backup probably. This is again I am acknowledging directly from one of the companies which works on it. I am sure my suggestion is that you look for it on your own, and then maybe contact them and follow them to the extent of this thing, because individual items they have it. Blindly copying one small part of it, it will only solve the problem so much. So, thank you. We will meet again in the next lecture. Thank you.